just happened that I actually know him. So Dr. Nikodem Szpak did his master thesis at Jagiellonian University under Professor Bizon, working on partial differential equations theory. Then he did his PhD, as far as I know, in Germany at the Goethe Institute about spontaneous particle creation and time-dependent over critical fields. Then he did his first postdoc at Max Planck Institute in Potsdam, where I happened to meet him, and now he works at the University of Duissburg-Essen, and he will tell us today about the analog models of space-time curvature in lattice systems, deformed graphene.
Okay, thank you very much for the invitation, and thank you for coming. Yes, I would like to tell you about what we're working on, different analog models of space-time curvature in lattice systems, and I will concentrate. So there are different systems we are looking at. One of them is deformed graphene, because it is very suitable, well suitable for this task. But we also look at other systems like optical lattices. But it would be, and others, but it would be too much to pack everything in one lecture. So I decided to concentrate mainly on graphene in this talk. And it happens that also today another talk has been scheduled in the BEC seminar at 2 p.m. And then I will talk about optical lattices. And if anyone gets attracted by the subject, feel welcome to come later. Okay, so. These are my collaborators. Can you see this? Okay. And at my university and in Mexico. So let me motivate why is it? What are analog models and why do we need them? So the idea of analog models is the following. So we have different physical systems which behave in a similar way because they have same or very similar mathematical description. This is always true in a restricted regime of parameters, of course, because these systems are truly different. It's not possible to map exactly one-to-one. So of course, everyone doing this must be all the time aware that it cannot exceed some natural boundaries of the parameter space. This is the critics which we hear very often, that when we do analogy, we make a fake, we prepare a fake system, we study the fake system, so we are aware of that, and still we can learn a lot. Okay, so the idea it comes from mathematics. When we have the same equations, we have the same solutions. Okay, and in the physical terms, it means when we have the same model, we expect the same effects. Okay, or some mapping of the effects. Which advantage do we get by this? We have actually the most essential for us is that we get access to regimes of parameters or to phenomena which are inaccessible in direct experiments, like very strong fields, mainly, and also precise control of parameters. Very strong fields are especially the case in gravitation, because we don't really have laboratory access to strong gravity. And in optical lattices, we can simulate materials and the advantage is that the scale is different and we can manipulate single sites and many parameters which in solid state physics are just given and cannot be switched off or changed. Okay, but in this talk I will concentrate on gravity. Gravity is curvature. And on top of this, we will look at quantum fields. Okay, so there's a clear advantage we don't have. We have no experimental access to quantum fields living in curved spaces. We cannot create strong gravity because we cannot move large masses. We have the nearest source of strong gravity is Sun, but due to its large size, we cannot just make precise quantum field experiments there. We cannot fly to a black hole and perform experiments there and come back. So this is a difficult field. We just can observe something from a distance that we'll probably not see directly any quantum field phenomena. or okay, not directly. Okay, maybe in some sense. Okay, so the realizations of gravity are various. So gravity means that we have space or space-time curvature, which we describe by a metric. And what the metric does, the non-trivial metric measures essentially distances and angles in kind of distortions of space or space-time, some sense similar to elasticity in materials. What it essentially does is inhomogeneous and anisotropic propagation of waves, or propagation speeds for whatever waves we have there. And the most common or systems where this can be studied are fluids or condensates or metamaterials. In fluids, we look at sound waves. In metamaterials, we look mainly at electromagnetic waves. But here, this is a different material. There's graphene. Okay, as I said, optical lattice will come in the second part. Graphene has this advantage that this is very elastic and can be very easily stretched and deformed.
Something I don't understand it. I mean, any solid is inhomogeneous and isotropic.
Yeah, sure.
All these properties you mentioned, you don't need to have a metamaterials.
Yeah.
I mean, metamaterials in contrast are perfectly ideal because we construct them such that
Yes, okay, but what I want to have.
Let me finish.
Okay.
That the lattice of metamaterials is perfect.
No, it depends. I can have metamaterials in which.
I mean, because
No, I can have materials in which the propagation of electromagnetic waves depends on the direction or something.
but the lattice, the structure, geometrical structure of metamaterials,
Yeah, okay.
because it's manufactured
Okay.
in the lab, it's not the failure of the matter nature which caused this.
Yeah, but this is okay. But this is not essential. Essential is if I have the properties such that I can observe phenomena like those which are generated by the metric in curved space. Okay. Okay. So let me. But as a byproduct of this whole idea that I take a system and simulate gravity, if I map system A onto B, at the same time I map B onto A. And in the case of graphene, there happens this funny thing that I also win something for graphene, because very many people get attracted by graphene for different reasons, and some phenomena are difficult to study in graphene. We map graphene onto a curved space, but we can also use methods. Analytic methods, solutions, our understanding, whatever, everything what we have developed in the last 100 years. And we can map it back to graphene and make predictions for graphene and say, maybe we have some better understanding on predictions for graphene. And I will show an example at the end to how what I mean. So for one of these applications is an efficient mode of transport, of quantum transport in deformed graphene. This is a very involved computational problem, because in small probes, or like 1 micrometer squared, we have 10 to 7, 10 to 8 atoms of carbon atoms in graphene. And this is computationally difficult to simulate the properties of such material. If the material is regular and periodic, it's always much easier, because one can look at smaller cells and then by using periodic boundary conditions just extrapolate the results or generalize. But when we have deformation like here and want to know how the current will flow or what the connectivity will be between different positions, it starts to be
Electrons moving into the
electrons.
lab.
Yes.
That's what you mean by the current.
Yes. Sorry. Okay. So I will tell you step by step, but this is just a general picture. We go from lattice to a continuous limit, and then we use this as an analog, but we can also make the opposite. Okay, so just for those who don't know graphene so well, as graphene looks like this. It has this hexagonal lattice, which is built of essentially two triangular lattices. One is the red one, one is the blue one. So the single cell is a supercell containing two atoms. Each atom has three nearest neighbors of a different type, of the opposite type. And okay, this is a material which is, in some sense, complicated. We extract from it the simple properties, and one of them is the effective description of electrons hopping from one atom to the other. We have an p orbital, or p orbital free at each side, which is perpendicular to the. There's essentially no difference. This is. No. The point is, the hexagonal lattice is not a lattice in the sense of crystallography, right? Because I cannot obtain it by translating the atoms by. It's not periodic. Okay? So I need at least take at least two.
We are actually having two interpenetrating triangular lattices.
It is like this. It's exactly like this. Yes. Yeah.
But the physical, this is a carbon atom. So what is the difference?
No. The difference is in the effective description. I can stay like this. I can ignore this.
Let me know, independent of a graphene, that the hexagonal lattice can give you like this.
Yeah, sure. And I will use this.
Peculiar about the
No. I will use this fact later. Okay, my effective model looks like this. That we introduce a basis of localized wave functions, localized around each atom, and write the Hamiltonian, the Schrödinger equation for the electrons in this basis. So these are the basis vectors, and they get the index A on B, because I always hop from A to B and from B to A. Okay, and this is important because this introduces a kind of matrix, and I will be able to switch to a two-component wave function. Okay, one describing the sides A and the other decides B, by which I obtain the Hamiltonian in the form 2 by 2.
But this, I'm trying to figure out why do you need two colors. These are nearest neighbors.
Yeah, this is my way of counting. Yeah, sure.
Hamiltonian always describes
Jump
between the between the nearest neighbors.
Sure.
So.
Yeah, but I will use this fact for my analogy. I want to construct.
Where there is no jump between blue and blue atom.
No.
Whatever you call it.
No. But I can use it in my description. I can, in my description, divide them,
but
and
vectors D1, D2, and D3 are degenerate.
Yeah, sure. There are sure.
The jump in the direction D1, D2, and D3.
At this point, no, but this will change. Okay, when I deform it, it will change. Okay. Okay, so this is essentially the reason why. I don't have all these calculations, but this is the reason why I can introduce a wave function which has two components and captures, okay, a single cell like containing both atoms. Yeah, the components will be psi1, psi2 first, but then later on it will turn out that this is a spinor. This behaves like an analog of a spinor. Okay? Because I will end up in a Dirac equation.
But it is the wave function of an electron?
Yes.
Or a charge or whatever.
Of an electron, yes.
Jumps, right?
Yes.
Okay, so how do you build up that spinor, as you said?
Okay, so. Yeah, that's.
The very essence of a tight binding, that they have something here and here which are, in some sense, independent.
Yeah, so the idea is go to. Okay. Yes, of course. These are Vannier states, and from this description I can go to some other description. This is the different parameterization of the atoms. That from this I.
What is the psi A and psi B? These are the wave functions of the electron.
These are the basis, yeah, the localized basis.
So there's
yes.
no difference between B and A.
No, this is just my numbering. I can. This is odd and even sides or something like this. I can always.
Also sum over P somehow.
Yeah, there is this HC. Yeah, this contains the other one.
Never mind, the sum is
No. The sum is correct. No. The sum is correct. I go.
Sum is over on A, then there is an index P which is free.
No.
Because
This.
it's a sum over A and a B.
No. You don't understand. I go. This is a symbolic notation which I can explain to you. Okay.
I mean, if we are going to understand the procedure.
No. This is not. Okay. This is not a rigorous paper. This is just just I can explain you everything if you like.
It's just a type binding, so instead of A and B, you should.
If I can comment a little bit,
Yeah,
you
sure.
start from the general Hamiltonian
Sure.
with the kinetic part and the potential part, and then you adopt the block theorem, then you will find that you have two independent bands. Okay, one band is a blue one, and the second band is the red one. And therefore, since there is no gap between these two bands, therefore you have to take them both into account when you do any dynamics. And this is the reason why you have two colors, because you have to take into account two bands simultaneously. And this is the reason why in type binding approximation you need to take into account both bands at the same moment. Okay, and we have these two bands plotted on the right-hand side. And this is the difference between standard optical lattice or standard lattice and this kind of lattice, because in this kind of lattice there is no gap between two bands. And this is how they start.
Okay. Okay. This is not something what I wanted to go into very much details because this is the standard book on graphene. So I mean there's a trick. Okay. I agree with you that all the atoms are equal. Are on the same footing, but I can renumber them in a way that I can artificially divide them into A and B, and then introduce a new wave function which is capturing always two sides. Okay, and this because I'm hopping from A to B and from B to A, the Hamiltonian will then this term will more or less have this form. Okay, I have the sum of diagonal terms and 0 on the diagonal. Okay, and this is just the trick. How I get after some calculations to something what looks like a Dirac equation. Okay, but I'm not ready now to show the details because this is the standard textbook on. Okay, but whatever happens, we end up in this famous band structure for graphene, which has these conical points. Here we see 6 conical points, of which 2 are physically different, and the rest are the copies of them due to symmetry. So when we look at the so-called K points, the dispersion relation is linear around this. There's a factor which is called Fermi velocity usually, okay, quasi-momentum, and there's this vector which is pointing to the conical point. Okay, so what people are interested in is just to look at the low energy excitations around okay. At the same time, this black here, okay, this energy 0 at this scale is a Fermi level. So automatically, when you look at energies with low energies, excitations with low energies, we are in the regime where the dispersion relation is pretty well conical, and then for this I can derive Hamiltonian, which looks pretty like the Dirac in two dimensions. Here we have sigma matrices, Pauli matrices, and this material factor, Fermi velocity, and derivative, and still this vector. This vector at this moment plays no role because this is constant, and since this is constant, it can be gauged away, can be introduced a phase to the wave function, which can be removed. But later on it will be interesting when I start to deform the material. What is interesting is that this factor, okay, this system behaves in some sense as these excitations behave as, you see there's no mass term, so these excitations behave like massless Dirac fermions, and in 2 dimensions. And the speed of light is not the true speed of light of nature. This is a material speed, which is speed of light divided by Rayleigh 300. Okay, that's it. Okay, and then now appears the very interesting questions to some people, like me. What happens when I deform graphene? When this analogy, when this description is precise, and many people have tested it in different experiments, and it's okay. What happens if when I deform graphene? Do I get coupling to this deformation field, or is it like coupling to curved space, or is it different? Okay, and this is the topic of. Okay, so what happens when I deform? When I deform graphene, let's imagine an so-called out-of-plane deformation. For 2 dimensions, I can think of out-of-plane or in-plane deformations. This out-of-plane is kind of mathematically simpler to describe. I can introduce a height function, which tells me how much I lift the atoms from the original position. I can kind of parameterize it, whatever I like. And then what happens when I move the carbon atoms away? The overlap of the localized wave functions will be different. And since they are anyway exponentially decaying, there will be some exponential effective or approximate formula which will tell me how much the hopping probability or the tunneling probability will change. And there is a kind of experimentally found or numerically found approximation that the hopping parameters which I had here scale with the change of the distance. So here we have the true distance between the neighbors and -1, which is just in this, we use units in which the original distance is 1. And there will be some material factor beta, which turns out to be something like 3.37 from simulations and from experiments. And I plug it here and do several approximations. And one comment here, there are 2 effects essentially. When I deform, okay, for Lattice, it's obvious that the cylinder is a surface of no curvature, but for many people it has. Okay, so because curvature has something to do with internal geometry, but this embedding is in materials. It has already an effect. When I have graphene, and in flat graphene I have atoms. I don't know if you can see this, and my orbitals, or my electron orbitals, look more or less like this. If I bend it, okay, it's exaggerated, but then the angle changes and the overlap changes also. So there will be some contribution from the bending itself, but this is subdominant. This is not the only thing. The other thing is that we change it when we stretch or deform. We change the distance. No, but yes, that's true. But yes. Yes, I keep. Okay, that's a good point. I keep the Vanier functions the same as I. No. This is my basis. I can. No. This is a. You can choose whatever basis you like, right?
Not let me finish, then you don't know what to answer.
Yeah, I know what you want to say.
You know what to answer.
No. I think you want. Because I.
Discuss with you.
No. But.
Clearly a power of clairvoyance. So
No. I think everybody asks the same question at this point. So that.
But I'm not animal. I'm Lucas Tursky, and so I don't like this kind of concept.
Okay. But you asked the question.
Different seminar here. We are not anybody. We are distinguishable.
Okay, I agree.
So if you are you willing to accept the questions?
Sure. I thought you asked this question. I got it.
No, I have.
Okay. So.
Go ahead.
Okay. Yeah, we can discuss after, because when we have so many interruptions.
Then there's no point of sitting on a seminar if I have to discuss this afterwards.
Okay. Yeah, in some cases yes, in some cases not. But okay, but coming to your point, I can choose my basis in a way. No. You said that the Vanier. Okay, to the point I have understood. Okay, to this point I have understood that the Vanier functions will change. One can look at this, one can change the Vanier functions, and then the situation will be even more complicated. But I can, in principle, in quantum mechanics, I'm free to choose whatever basis I want. So I keep the original wave functions. Okay. But I only just shift them, just exactly as the atoms shift. Okay, and this is a well-defined procedure. Okay, so yeah, then what happens to these light cones?
Guarantee that your true system has any overhanging projection on this basis, because this is not a set of states that you have.
Yes, okay, yes. If I do this construction, I'll need to take into account that this system can lose orthogonality or completeness, and I will need to account for that. Yeah, sure. Yeah, okay. I could make a lecture on this, but this is just the introduction to graphene. And sorry, I didn't think about that. This will be relevant here, and yeah, this will take a lot of time just to explain all the mathematical. This can be done in this.
Has nothing to do with the graphene altogether. You have a simple expression on the board, which is the Hamiltonian on a lattice. It's a mathematical object. Now you are deformed that lattice, and the question is how the deformation of the lattice affects the time-binding Hamiltonian. The problem is solved since 30 years at least.
Yeah, okay, but
And it's known how this expansion should be done.
But, okay.
And it is not what you are discussing.
yeah, but I have some freedom.
That's my
Okay,
goal.
okay.
That
But-
the expansion of this Hamiltonian
Okay.
on the curved lattice is extremely well done.
Okay, but I have still some freedom.
Literature,
Okay,
which you don't give there.
okay. I have still some freedom of choosing my basis, and I choose this basis.
You don't. That's the point.
Okay.
This is a mathematical question. What to do if you have that Hamiltonian on a curved lattice? There's no freedom in it. You just have to do the mathematics.
No, the Hamiltonian written as this is with respect to basis.
Deform the lattice. The question is what is meant by deforming the lattice. And
Sure.
it's not only that you have to change the
Okay, so
element t, which is actually because from where the dependence of a t on the distance comes, from the overlap of the function.
Sure.
There's the integral. which
Sure,
is
sure,
fancy.
sure.
You have to have the wave functions of the
Sure.
object sitting in one place and
Yeah,
you
I agree.
calculate the overlap. There's nothing mysterious in it.
yeah, I'm saying the
So
same.
it is known, but there is another term there, which is crucial, and this sits in the expansion. That's what is written on the board as FCD n plus D and L. Because the D and L, which sits there, what is meant by this n plus D and L, that's the crucial point of the expansion of the time-binding Hamiltonian of the curve.
Okay, but-
And that is the point.
Okay, okay. And my point is that I have mathematical freedom in choosing the basis.
The question is you don't. That's-
The analogy would not work, so we have to cheat some.
No, that's not cheating. This is mathematical freedom. No.
Excuse me, what kind of analogy?
Well, this is what we will.
Well, if you are talking about the analogy with the gravity, it will hold if the mathematics is done very perfectly, and we are just
Yeah, I agree.
the 50 years of how that was done correct.
I agree, but
I even brought a book.
I will make a short comment on this, okay? Because I agree that there is no freedom to choose the basis. However, in the perturbation limit, when you are in small deformation limit, then wave functions are perturbed in the second order perturbation. And this t is perturbed in the first order perturbation. So as long as the perturbation is very small, then this approach
There
is
is a
correct.
question, what is the small parameter?
So this
The
I
whole
agree,
problem
yes.
is that there are two small parameters in this model. The one which is referring to the t, and the other which is referring to the curving of a lattice. And the expansion of the Hamiltonian is not trivial because it involves two parameters, and you have to do very carefully keeping
Yes, I
track
agree.
of what is the order of the expansion of what. And you cannot just keep one expansion going on to the order n and the other to the order m.
I agree, but in the small, in small curvature limit, the first correction appears in tunnelings, not in the Wannier functions. This is only my comment, okay? But I agree
But
that
the
there is no
question is
freedom to
that-
choose.
But the question is that the word is meaningless here. There is no small curvature. The curvature is the geometrical object which is appearing in a properly handled time-binding Hamiltonian in its full glory.
Sure.
differential geometry, which is a portion.
Sure.
So the question is much more complicated, and this hand waving saying that there is some expansion. The curvature
Okay, I can.
cannot be expanded.
Okay, I can.
The graphene, when you bend it, it has a certain curvature. That's it.
Okay, I would suggest that we sit down after the talk and go through all the details because it will take hours. I think this is maybe not very interesting to everybody. Okay. Okay, there will be small parameter. The small parameter will be the strain, the measure of the variation of the distances of the atoms. And then I will propagate this parameter through all these calculations. And these calculations are done, but not on the foils. Okay, so let me continue. So what happens with the dispersion relation around the cones when I look at it, when I strain graphene? What happens are two different. So essentially, what happens is the picture. These are the cones shown from above as a top projection. So the cones get deformed and get moved away from the original points. And this will affect in coupling of the effective continuous equation to two new fields. So one will be a vector field, which describes the shift. And as you see this, as I said, there are two different types of the cones. So you see this cone, and this cone behave in exactly the same way, exactly as this, and this. Okay. So one vector field will couple to will describe the local shift, and the other field will describe the deformation, and this will be a tensor from which I will be able to construct the metric, which will be related to the metric. So the effective equation looks like this. Sorry, I don't present you the derivations, but I think this will really explode the scope of the talk. So the effective continuous equation looks like a Dirac field in two dimensions coupled to curvature and to magnetic vector field. So this vector, which I told you about, is now position dependent and couples like a electromagnetic vector, in this case magnetic vector potential, because in two dimensions the magnetic field has one component and it's a 2D vector. And here comes something what material people call anisotropic Fermi velocity, or correction to the Fermi velocity. But in relativity or in field theory we call frame. And this frame can be used to construct the metric, the effective metric, which we don't see exactly directly in the equation, but this is how the Dirac field couples to curvature. Okay, and when I have strain, the strain tells me how much I change the distances between the atoms or the angles, and this strain is encoded in the strain tensor. So this is what comes from the Cole calculations, that the frame, that the new frame, that the effective frame is the old frame, which is trivial, orthogonal, or orthonormal.
Here comes this double expansion, because if you do this, you also have to replace the derivative. The mathematical,
No.
do it correctly, it's not only the, as you call it, the main vector or the local vector, which will be expanded, but also the derivative. And this equation not necessarily will be that of that form.
It will be because I don't make this procedure that I go from continuous equation to here. I start from time binding. First, what I first did in the flat graphene, I go from time binding, homogeneous, okay, regular, and end up in Dirac, flat. But now what I do, I deform. Okay, I don't make this step. I first deform, time binding prime, and now I do analog derivation, low energy, long waves, several approximations, and then this is Dirac plus G. Okay, why not?
Because that is done in literature, and that's not correct.
Yeah, this is also done in literature.
I'm sorry.
Okay, we can maybe.
This in some very special situations.
Okay, Okay, there will be further terms. Okay, there will be plenty of terms. There will be terms which I should have written here. There will be a term which is known in the field theory spin connection. It will also be here. And there will be also maybe some other higher order terms which we just skip because we.
Is that this Hamiltonian, this procedure you are writing here, indicates that the Hamiltonian is covariant. That your expansion makes the Hamiltonian into quasi-relativistic word covariant because this equation transforms. There will be non-frame invariant term in this expansion, which is important.
Yes.
Because it governs the scattering process.
Yes. Okay.
That's the point.
Okay. Okay. What do we have? Okay. Here we have plotted the deformation, and here you see with the color you see the Ricci or Gaussian curvature, and here we have this vector field, this K. All fields. Once I know the deformation tensor, the strain tensor, I can derive all the other fields from it. This is the standard way as people are looking at such systems. One can parameterize in a different way, but this is just one way of looking at this. So this vector field looks like this one here. You see the arrows, and if we calculate the rotation of it, we get the magnetic field. As I said, this is a single component field, and you see the colors here. This interpolates between positive and negative values because the arrows rotate in left on like clockwise or anti-clockwise. So this is the standard for radially symmetric deformations. This is the standard form of this what we call pseudo-magnetic field because this is not true magnetic field. We can also impose a true magnetic field on graphene, but in that case this is an effective magnetic field which the electrons will feel, but this is not real. We cannot measure it by an independent apparatus that it is outside. What is important is that I have these two types of valleys, or so-called valleys, and this couple in a different way. So maybe I should have written this S index is responsible for that. So they couple with plus and minus. So one goes to the right and the other goes to the left by the same amount due to symmetries which we have in the system. So one cannot now universally say if there is a magnetic field which has a given sign. No, the sign couples differently to these two types of valleys. Okay, so there are further formulas, but let's skip it. But now we ask the question. Okay, so we have curvature, very nice. So what can we do about this curve? How can we kind of convince ourselves that this all works and makes sense? And are there any effects or predictions or whatever we can do? So people have looked earlier at the density of states. That when I deform a material, that it will be the electrons will rearrange in this material such that the density of states will be different. But the density of states is not something what is really spectacular or really essentially following from the Dirac equation. If I introduce a local electric fields, I can also manipulate the density of states. So this is nothing special. And so we looked. So actually, what is curvature essentially? So for me, curvature is when I observe that two parallel lines cannot stay parallel. Okay, they either start to cross, or go away from each other. So, but in order to have this, I should kind of go from field theory to trajectories. So then we started to look at trajectories by performing something like a geometrical optics approximation for this Dirac field, and to look at what will be if I send a plane wave through the system, how the rays will flow through it. So these are the steps, also only just headlines. So we start with the Dirac Hamiltonian, square it, go to kind of Klein-Gordon kind of equation for scalar wave function. Then we need, I guess, to skip again this higher order terms, and then yes.
How come that the Klein-Gordon equation comes into the game? second order?
Yes, we square. Yes, square the Hamiltonian.
What kind of what kind of adaptations is in your Klein Gordon? The Klein Gordon
Yes, this will be.
What
Yeah, sure.
Is it a normal Laplacian?
No, this will be.
Beltrami. So which one is coming then?
Yeah, this is the Laplacian in the curved space. Yeah, sure.
Have your Klein Gordon equation? What replaces the second order differential equation?
Yeah, so essentially you get the G, let's say Ij in that case, and here you have covariant derivatives.
That is certified.
And no, but you have other terms, okay? You have other terms which
This derivatives are different. I mean, the people working, the point
No.
is that you are, there's an enormous
I did this calculation. You can just square and you will see what comes.
physics devoted to dislocations theory.
But we are in elasticity.
How they deform lattices and how the electrons propagate on them has been studied in a greater detail.
I know.
Light frequency to the many others.
Yeah, I know.
That this Klein Gordon is exactly different.
No, there is a part which behaves like this.
Yeah, but the physics does not depend on how you derive it. The physics is the mathematical issue. There is a time-timing Hamiltonian, and the rest
Yes, I agree.
should follow unambiguously. And that has been mathematically done.
No, I can show you the calculation. This is very simple. You square this and you obtain some expression. And you can pack this expression to this and some other terms of higher order in my deformation. Okay. Yes, and I know these papers and I cite them and okay. Can I continue? Okay, then for this scalar wave equation, we introduce something what is usually done in geometrical optics, this aconal approximation. We replace the wave function by a pure phase. And then look at something like velocity field. So we look at the gradient. And then we can integrate the velocity field and obtain trajectories. Okay, this is the standard way how to. Yes.
If you parameterize
Yes,
the
yes,
velocity field
yes.
as a gradient of a function, it will be just potentials, no way of potential.
Yes, this works for small deform.
Okay, so
Yeah. That's,
thanks.
okay. So and it turns out that the equations will have this it will be possible to bring the equations in this form. So this is the geodesic part. Okay, we have the true Christoffel symbols of the curved metric, and on the right hand side, actually, I could have written here the Maxwell tensor, but written in 2 dimensions with only magnetic field. It's at some that form. But this is something like coupling geodesics. We have geodesics for something. What is okay? This is the equation. So how we interpret it is our thing. It looks like a massless particle, kind of coupled to magnetic field. Or I don't know. We have no mass parameter. These are always all material parameters. And okay, so what are the effects of these fields in the in this situation? So here we have only the magnetic field. So the magnetic field has this action that when I send some trajectories, they will just turn right, turn left, and right because the magnetic field, the sign oscillates. When we look only at the geometric part here, when the magnetic field is 0, then we have just geodesics in a positive curvature situation, just like bending of planet trajectories. And when you combine these two, so we arrive at trajectories like this. And then we ask the question how well this approximates a current flow. So whether we can find a regime. In the regime where then we need to be really careful. So one thing is, in order to work with continuous approximation and all, we need to look at wavelengths which are much longer than the structure of the crystal itself. But then, if you want to use geometrical optics, we again need waves which are much shorter than the geometrical structures. Okay, only then the geometrical optics gives a reasonable approximation. But there is a regime in graphene. There is plenty of place the distance between the atoms is nanometers, and we can have wavelengths which have hundreds of thousands of these atomic distances, and then we can have macroscopic curvature structures which are on the scale of micrometers. So it can be done, but one has to really be careful. When one doesn't work in the proper regime, nothing works. And we did numerical simulations of that. So here's just first pictorial comparison between what we did. So here we have the trajectories. Here are different colors. So the black are the trajectories respecting both forces, and the blue and red are the trajectories in the case if one of the force were kind of artificially missing, just to see which force or which field causes which effect. And here we did lattice simulation. This is the language or the framework known as non-equilibrium Green's function method. We put contacts at the boundaries and inject current and look how the quantum current flows through the system, just calculating the wave function and current from it. Okay, and here are some examples how it works. Here is just a top view. Depending on this is a rotationally symmetric kind of, but there is some mismatch between my screen and so you see a broader picture. So this is actually a rotational symmetric in a discrete sense in the same. So here we see the colors show. The red one is the current, is the quantum current density. Okay, the quantum current is the vector field, and we calculate the density of it, or the length. The yellow ones are the integral lines of this quantum current, and the blue ones are the predictions from the classical calculations from the geometrical optics. That we say we start with trajectories just orthogonal to the boundary, and just integrate them in these classical fields. And we see that in this regime, and on these pictures you see different height of the bump. Here's flatter, here's higher and higher. Okay, this is all the D0 is the unit of atomic distance. The radius is the radius of the bump, is always the same here, but the height of the bump varies by some factor. Okay, and we see it really works pretty well. So we have comparison between three different regimes. We have at one hand we have timed binding. Then we have as a kind of approximation we have Dirac plus metric plus magnetic field, and then we go to trajectories. Trajectories also in plus metric plus magnetic field. And then we compare this with that. Okay, and there are plenty of approximations on the way, so we are aware of that. But at the end of the day, in a good regime of parameters, it works. So we are pretty happy about that. We have gained some understanding of what's going on in these systems. Then we observed the funny thing, if I have time for that, that in some situations, the classical trajectories cross. So when they cross, the corresponding current, which is red here, stays very focused, because in general it should spread. When you inject it on a narrow contact, it should kind of spread. Even if this is a plane wave, it will have, this is just like a slit, okay, single slit diffraction or something like that. And then we started to think about some applications which could be interesting for some people, as something like lensing. Okay, we know from general relativity that we have gravitational lensing. So we asked the question: can we have lensing, geometric lensing in graphene, just only due to deformation? And we found out that there are situations when the raising is especially efficient, but there is one difference with the standard lens. The standard lens, the symmetric lens, usually works in that way that if it focuses plane waves, it focuses them in one point behind the lens. And in these situations, we have two focal points, right and left. And this is due essentially to the fact that we still have this magnetic field, this pseudo-magnetic field, which we cannot switch off. Okay, just if we hadn't this magnetic field, we would have this these dotted lines where we took account only the gravitational or the geometric part of. Okay, and here are some simulations. So here's a perfectly flat graphene, and here we inject plane wave electrons, and they propagate through the system in pretty homogeneous way. Oh, this is restricted by a Gaussian form. I guess this is not the ideal plane wave. This is a Gaussian form beam, more or less, but it stays pretty focused, yes, as is known for Gaussian beams. But when we increase the height of the bump, we see these two focal points start to build. Okay, but then this works pretty well. And this is not all. This works well for one valley, because as I told you, there are these two valleys. So my electrons have two kind of degrees of freedom. I can eject in one valley or the other valley with the same momentum, with the same energy. And this couple in the opposite way to this pseudomagnetic field. So in one case, the trajectories will look like this, and the other case, the trajectories will look in a different way. So here we have injection at a 1K point, and these are the trajectories. And in the opposite situation, at a K prime, whatever, the trajectories cross in the middle. Okay, so when we inject a wave function which is a mixture of both valleys, we can take whatever superposition we like, we obtain something like a splitting of this, or filter, or spatial splitting of the valleys. So this is interesting for people studying graphene as a material, that one can separate the valleys. Usually there is not much control about it. Okay, maybe because the time is short, I will skip this part here. So okay, this can be used. Okay, so this brings us to the idea that one could propose a sensor, very precise, very sensitive deformation sensor, which, if I am able to measure the contrast between the currents flowing to these outer positions and to the inner one, and I could manipulate the valleys, I could, by having the contrast, I could tell how much the graphene is deformed in a very precise way on a nanoscale. So okay, let me skip this. This is not very important. Okay, like this. Okay, so we end up with the following picture, that when we plot the contrast between the currents, let's say, as I shown here, outside, flowing outside and flowing in the middle, depending on the bump height, I will see a clear change of the intensity of the currents at the different contacts. So by contacting precisely on the nanoscale or micrometer scale, I could produce a yes. Okay.
So I should have seen it in the experiments on the conductivity.
Yes, but we have still no experiments on that scale. So this is still difficult, because it's difficult to control.
You look at what are the consequences of this geometrical length to the conductivity.
Yeah, sure. This is in a sense the conductivity between different contacts. Yeah, this is. But you mean experimental or theoretical? Experimentally, it's difficult to do at the moment. Yeah.
If I take a piece of graphene, bend it a little bit, and send the electric current through it, then the only thing I can experiment, I cannot look at a single electron.
Sure.
So
this is.
I will never see. So how can I verify experimentally, even in theory, in the Gedanken?
Yes, like here. Like here. That when I place my contacts at the positions where I, from my trajectory point of view, which is my just. Yes, but it tells me where to place the contacts, where I should expect that the current will flow. Okay, you see, this agrees pretty well. So by knowing the trajectories, I can guess where to put the contacts. So I put this outer contact here and the inner contact here. Okay, this is my first guess. And I design my experiment and measure the contrast between the current outside and inside. Okay, the difference of the conductivity between the lower contact and the upper contacts. This is the trick. But now it's experimental, a little bit tricky how to contact materials on that scale and deform graphene at the same time.
I take a copper plate and I bend it a little. And I weld a point contact on the one side of the plate. Then that same effect will happen.
Well, you must be careful with the scales, right? This is on a nanoscale.
This seems to be the prediction.
No,
It's obvious that if there is a hole somewhere in the middle, then the electrons will flow differently than if there is no bump in there.
Yeah, sure. This is a play of scales.
Of your trajectories, it's obvious that the longer trajectory is over the hill and the shorter trajectory is on the left or on the right.
Yeah, this is an interplay of scales. If you are on a small scale, you know that the wavelengths play a role, and because this is kind of interference effect. Okay, if my wave flows around some.
What kind of a curvature, what kind of a bending I have to apply to the graphene in order to?
Yeah, graphene is very special.
To turn those trajectories around.
Yeah, just strain of a few percent, of 1, 2, 3% is enough. Sorry? No. Turn back, or what was the question?
You are calculating these trajectories.
Yes,
right?
yes. Mm-hmm.
The question is, if I bend it too much,
Mm-hmm.
then I turn it.
Okay, you should not say bend. You should say deform, because just bending like this is not.
I make a bump by deforming it.
Yeah, but I need to stretch kind of. Okay, because if I only take a sheet of graphene and bend, this is not the same. Okay, then I get a.
You create a hole in the middle. The
Yeah,
bump
kind of.
the middle,
In some sense. Okay.
that's
Mhm.
the same thing
Let's say that.
depending on which
Okay, let's be precise. Okay.
Okay, so if I make a bump, then the trajectories bend around. And can I make this bump sufficiently high such that your classical trajectories go to the side?
I think yes. Yeah.
Then you will have something like a Hall effect. Have you that I will
Except that this is symmetrical, left, right. I will have the same.
never mind, depending on these points K and K prime are not symmetrical.
Yeah, I have. Yeah, it's a good idea, but I have still the symmetry.
This magnetic field is fictitious. The force, the Lorentz is fictitious. Lorentz force is charge independent. That's why you have a symmetry case.
Yes, but in each case I have.
Once that there is no charge in this.
No, in each case I have left-right symmetry. So this Hall effect, it will not work between left and right. It will work between middle and outside. Kind of. If you. Yeah, this is a kind of. Okay. Okay, so I think this. Okay, there are also interesting situations with several bumps when the magnetic field is different and the trajectories just very nicely separate all the valleys. This can be studied as well. So let me skip this. And okay, as the last, let me maybe in the last 2 minutes tell you something about another system which is also made of graphene. These are the nanotubes. Nanotubes are actually older than graphene historically. And I can play the same game. I can take a nanotube and bend it, and then I introduce a strain which is a different sign inside, which is a compressive strain, and tensile strain outside. And I can play the same game as here, and end up with the effective metric for this kind of. This is now a part of a torus. The effective matrix has this form, whatever. There is a pseudomagnetic field again, and okay, pseudomagnetic field, which is approximately a sine of the phi, and phi is the angle inside. Okay, theta is the angle here, and phi is the angle like this. So the magnetic field will have the red is positive and blue is negative on the torus. So this is a funny system, because if I look at classical trajectories in this, they will be attracted to one side. Okay, if I send current along the tube, the one side will be attractive and the other side will be repelling. So So, and the nice thing about this system, I can solve almost exactly the Dirac equation with this metric. It can be separated, and in the regime, I need some approximations such that the inner radius is much smaller than the curvature radius outside. But for this, I can go from the Dirac to for some form of Matthew equation, and I can now expand my solutions to Matthew functions. And then I can look at several modes, at low energy modes.
You do not close this
No,
now.
I don't close. No. Well, actually, for the sake of the no, sorry.
Where is the mean
Wrong.
curvature of the tube in your equation?
The curvature, yeah, okay.
There's a mean curvature, right?
Yes, the curvature inside is
Except
negative.
curvature, what-
Yes, the curvature inside is negative and outside is positive.
But there must be a number. I mean, if I have a
Oh.
number, then if I take a nanotube and I bend it,
Mm-hmm.
then there is a number which tells me how much I bend it.
Yeah, this is the
There will be
strain,
a
yeah.
number in meters. So where is that?
I don't know in meters. I know the strain in percent. When you change the distances, you can say the strain in percent. But okay,
You have a radius of the tube. But
Sure.
there's another length. I mean,
Sure.
all it is that your metric information does not depend on the other length.
Which length?
Well, if I have a tube,
Yes.
it has a radius,
Yes.
which is r.
Yes. No. R is the
R is the external radius.
curvature. Yes, radius.
So
Yeah.
then where is the radius of the tube?
Yeah, here.
Rho.
Rho is this here. Here. Rho is the inner radius, and R is the outer. Yes, I said it. Okay, and rho divided by R plays the role of a parameter in which I can expand. Okay, and I have again here.
Rho is a running number, so there's no length there.
Okay, whatever. I can now compare and show that this again is a very good approximation and tells me something about the system. I have here the analytically found Matthew modes. This is the lowest energy mode, and here's the numerically found current flow that I put contacts on both ends and send a current, and find that the profile is if I cut my tube here across and plot here the intensity of the current, I see there is more current on the one side, let's say here outside, than at the inner side. And the contrast between the inner and outer side as a function of the total strain is presented here. So it saturates, but it very quickly goes to an extreme. So this is also a very interesting prediction, and it is not very easy to measure and verify it because one needs to very precisely put the contacts on a nanoscale system, and also in such a way that not to perturb the system too much, okay? Because we want to make a possibly invasive experiment. Okay, but that was all. Thank you for your attention.
I'm sorry,
Okay, just one short question regarding the third plot here. What is actually mapped here? It's a
Here?
potential, it's a magnetic potential by the colors. It's a magnetic potential.
Aha, the colors.
or
Okay, this
field?
is a larger picture. The color is the pseudomagnetic field.
Then I'm a little bit confused because according to the expression on the bottom, it should vanish at phi equal to 0, which is on the top according to the upper picture. So
Okay, I'm sorry.
slightly confused by
Okay,
the
I'm sorry for this. Probably this comes from two different calculations. Yes, but this is the proper one. So probably one should change the angle. So it starts 0 is somewhere outside or inside.
But then I
Okay.
end up with
So
blue
so
one.
or if you want to keep it like this, then
So
we
blue
need to do
is
cosine.
corresponding to 0 or
No, the upper side is positive and the lower side is negative. Okay, this
so
is the statement.
graphics is slightly difficult to interpret. Thank you.
Mhm.
okay, if there are no more questions,
Then I have a historical. It just so happens that we have 50-year anniversary of this little book which I brought with me. It's a book written by our late colleague from Warsaw, Marek Żurawski, published under the auspices of the André Lichterowicz, the famous French mathematician. It's called the Théorie mathématique de dislocation. 50 years ago, this topic of the relation between the three-dimensional curved and deformed lattices and general relativity was extremely popular. And in Germany, there was a full school by Eberhard Krenner. And there are still people doing it. You have this colleague of you in somewhere next to Essen who is doing this work. And this is still very much popular, this analogy between the deformed lattices and differential geometry. There is a huge Russian group of scientists doing it, Polov, Katanaev, and the others. And there is a Brazilian institute which does the study of it, like Mr. Furtado. And they are recently doing works on the graphene, and I'm getting lots of these papers for referring. Much. But anyway, this analogy between the lattice dynamics and general relativity is known since at least 50 years, and this is one of the most important books about it which exists in the literature.
But these are also different stories when you have dislocations and defects, but you're running elasticity here. Okay.
Dislocations are that there is difference in the integration of your equations. I mean, the problem with the issue which causes a problem is that what you are doing is what the solid state old-fashioned physicists will call the local potential approximation. And
no, there is more.
This scattering of electrons on the deformation of a lattice is a subject of thousands and thousands of publications.
Yes, but graphene is very special, and
the issue is that if you want to study this analogy, then you have to look at it slightly deeper into this geometry, and it comes out that it is not as simple as it looks like.
Okay, thank you for the
okay,
comment.
it's
Right.